Welcome back. So the next regularization technique that we are going to look at is early stopping, and this is a very commonly used regularizer, and it simply follows from this plot that we had discussed earlier, right? That if you allow training to increase, right, or the model complexity. Earlier we had seen this plot in the context of model complexity, where we had commented that as the model complexity increases, your training error keeps going down to 0, but your validation error may start increasing after a certain point, right? Now we are seeing this plot again, but in a slightly different context, where on the x-axis you have steps, right? The number of steps for which you are allowing to train the model, and on the x-axis again you have the error, right? And again, what is observed is that as you keep training for longer and longer, your training error will go down, right? Because you're allowing your parameters to move, keep changing constantly, and they'll keep changing, keep adjusting till they drive the training error to 0, right? But while doing so, they will end up overfitting on the training data, and there will be a huge gap between the error on the validation or the test data and the training data, right? So a simple way of avoiding this, and our goal of course as usual is to find that sweet spot where the training error is also low and the validation error is also as low as it can be, right? So that's the sweet spot that we are looking for. Perhaps in this example that sweet spot is somewhere here, right? Or, yeah. Okay, so then what is typically done to avoid this kind of overfitting, where you're training the model for longer, is to do this early stopping, and we'll see what early stopping actually does. So we track the validation error. So you're tracking the red curve along with the blue curve. Now have a patience parameter P, okay? So now I'm tracking the validation error, and I have a patience parameter P. So what I'll do is, after P steps, or this patience parameter can be defined in terms of steps or it can be defined in terms of epochs. So after P steps, if for P consecutive steps, right, my validation error is not decreasing and it continues to increase, or even if remains monotonic, then I'm going to stop training, right? Because my training error is decreasing, but my validation error has been increasing for P consecutive steps now. That means something wrong is going on, right? So at this point, so what happened is I was tracking validation error. Let's see what is happening here. And after every, like in a moving window of P, I am checking whether the validation error is decreasing or not. So in the first window of P, I don't have a problem because the validation error is decreasing. Then I move the window by 1, again there's no problem. Again I keep moving the window, and till this point I don't see a problem. But now in this window of P, there have been P consecutive steps, but my validation error has not decreased, right? So now I'm going to stop training. Not just that, I'll go back and just retain the model which was there at step k minus p, right? So I'm currently at step k, and I've observed that the past p steps the validation error has been increasing while the training error has been decreasing. So I'm going to throw away the last p updates that I have made, and I'll simply take the model which was there at step k minus p, and I'll release that as the final model that I had, right? So that's what early stopping does. It has this patience parameter, and I'm stopping training early. I'm not allowing it to keep running till it drives the training error very 0, because I know there's a consequence that it will overfit on the training data and my validation error would be high, and I've defined this window of P over which I keep tracking the validation error, right? So that's all that you do in early stopping. And now what we'll see is we'll look at some analysis of this, and we'll try to build some intuition about how in some sense this is equivalent to L2 regularization, right? So we'll try to do that, but let's just this is exactly what I just said, and you are stopping the training early, right? And this is very effective regularization technique, and one of the most widely used, because it's very easy to implement, right? Just let the training happen, no changes to the loss function, nothing, and you just let the training continue. And whenever you see that, okay, validation error has been constantly increasing, you can automate this and just say that stop whenever for the past p steps my vector is having values which are monotonically increasing. It's very easy to implement, right? And it can also be used with other regularizers, right? So you can also have the L2 regularizer in the loss term, in addition do early stopping, that apart from the L2 regularization, you are also tracking the validation error, and if there is a patience of P has been exceeded, then you stop the training, right? Now, how does it act as a regularizer, right? So, we'll first see an intuitive explanation and then try to do a more rigorous analysis as we did in the case of L2 regularization, right? And both the intuitive explanation and the rigorous analysis will try to make a case that this is in some sense similar to L2 regularization, right? So, first we start with the update rule. This is the update rule in gradient descent, and it is a similar update rule in most variants of it, right? When you take the compute the gradient, and then you either have the momentum term or an adaptive learning rate, but at the crux of the problem is that you are going to start with some initial weight and keep updating it based on the gradients, right? Now, so if I were to look at starting from the initial time step, what is the weight at time step t plus 1, then it is just the initial weight minus the learning rate multiplied by all the consecutive gradients that I have computed from step 1 to step t, right? So, I have just written the formula in a different way, and there is nothing wrong here, right? I am just saying that instead of expressing it as Wt minus the gradient at time step t, I can just keep track of everything that I have done. So, I started off with W0, then subtracted W0 minus eta times W1, then this was my eta times the gradient at W0, this became W1, and then once I had W1, the way I computed W2 is again subtracted eta times W1 from it, and this became my W2 and so on, right? So, all of this I have put inside a summation now. So, this is how I am expressing it, okay. So, this is what you are doing. Now, across all these time steps, right, so you had the derivative at, so there are t terms here, right, and let the maximum value of any of these gradients, let me call it as tau, right. So, you have t terms here, so each of these gradients, so this was delta W naught, delta W1, all the way up to delta Wt, and I am saying the maximum of this set is tau, right. What does that mean? It means that each of these quantities is going to be less than or equal to tau at best. Okay, that is what it means, right. Now, if I want to comment about this sum now, what can I say about the sum? It has t terms, and each of those terms is actually less than this tau. So, the sum itself is going to be less than equal to t times tau, right. It cannot be greater than this, right? That's all I can say that about this sum, right? And that's exactly what I am going to do now. Yeah. So, now if I were to look at the difference between Wt plus 1 and W naught, then at max it's going to be this, right. It's going to be less than this, right? That's all we are saying here, right. Now, what does that mean, right? So, if this t here, right, that is the number of time steps, is actually controlling how far does Wt go from the initial W naught, right. So, every time I am doing an update, I am changing W naught, right. So, now the more times I do these updates, more I am going to change W naught, right. So, I started off with some initial W naught, and at every time step I am moving away from it, right. And so, of course, some time steps I might even move back, but let us assume every time step you are moving ahead, right, moving in some direction farther and farther away. So, this is actually controlling how far you are at time step t, right, the number of time steps that you have. This was 1, 2, 3. Now, in early stopping, what are you doing? You are controlling the number of time steps for which you are going to allow the training, right. You are controlling this t. T here is the number of steps, and you are doing early stopping. That means instead of training for million, 10 million, 100 million steps, you are going to stop at some point, right. So, that is going to determine how far this Wt can go from the initial value, right. And that is exactly what you do in some sense in L2 regularization also, right. You start off with something and you are drawing these boundaries, right. So, you are, if you remember the contours of the L2 regularization, this is how it is, right. So, it actually tells you how far you can go from the initial weight that you had, and here also the time step t is actually controlling how far you can go from the initial weight that you started off, right? So it's also in some sense shrinking the weight because it's not allowing the weight to grow very large. The more you update, the more the weight would grow, right? Yeah. So that's why it's like intuitively similar to what happens uh, in L2 regulation. It controls the space of exploration, and the same thing I had shown those contours. So L2 regulation was also controlling that space of exploration. Right? Okay, so now let's look at a mathematical analysis of this. So we'll do a similar derivation as we did in the case of L2 regulation. So we'll start with the Taylor series approximation. So this is what the Taylor series approximation was for W, which is in the neighborhood of W star, right? And remember, W star was the optimal for the LW, which was the unregularized loss. This was the empirical training error, right? Which was, I don't know why this. The squared error between the true value and the predicted value. This is what LW was. And so this is what the Taylor series approximation stays. And if W star is the optimum, I am again going to use the property that the gradient at the optimum is going to 0. So now I have a way of expressing LW in terms of LW star, which is the following, right? So I've got this formula. Now, if I take the derivative on both sides, so if I take gradient of LW and, so just take the derivative on both sides, and I get the derivative of LW star is actually H into W minus W star, right? And we had done this earlier. You could think of this, so I've just put a delta here, right? So this would again become 0, and then you have the derivative of this quantity. You could treat this as a square quantity, so it would be 2 times W minus W star into H, and that 2 will cancel and you will just be left with H into W minus W star. Okay, so nothing very difficult happening here. Okay. So now the SGT update rule would be Wt is equal to Wt minus 1 minus the derivative of the loss function, right? So this is again the derivative of the loss function, right? Sorry, this should not have been W star, this should have been W only, right? The W star was here and that becomes 0, so this is only W, right? So these two quantities are the same, right? So I'm just going to replace the formula that I just derived here. So again, remember, this was the derivative of the loss function evaluated at Wt minus 1, right? And I just got a formula for that here. So I'm just going to substitute Wt minus 1 in that formula. So this W will become Wt minus 1. Everything else remains the same. Okay. Again, just as I was doing in the derivation for L2 regulation, these are just like one step after the other. It's just substitution of formulae that I have previously derived, and we'll keep doing this till we reach a point where we can make some comments about what is happening, right? So now I can just rearrange the terms. So I have the two Wt minus 1 terms, just as I had done in the earlier derivation. So this is Wt minus 1, and I can just write it as I into Wt minus 1, because Wt minus 1 is a vector and multiplying I by any vector remains the same vector. So if I do that, I can write this, and then this becomes like a valid matrix operation because this is also n cross n and this is also n cross n. If I don't put the I there, it becomes 1 minus something, which does not make sense, right? So I've just rearranged the terms. Okay. So this is what we had on the previous slide, right? So Wt is given by this formula. Now again we are going to use the eigenvalue decomposition of H, because we know that H is positive, semi-definite, it's a symmetric matrix, so the eigenvalue decomposition exists. And not just that, we also know that the eigenvectors are orthogonal, so Q inverse is equal to Q transpose, that's why we get this form. And now in the previous equation, I'm just going to substitute in this equation. Wherever I see H, I'm going to substitute it by Q lambda Q transpose. Okay, and again I'm just going to rearrange the terms a bit. Okay, so now if we start with W not equal to 0, right? So remember that this is a recursive formula, right? So if I start with W not equal to 0 and we have this derivation at the end, so we just do this by induction. So you start with W not equal to 0, then you assume that this exists for W time step t, and then by induction you can prove that this also is true for time step t plus 1, right? So what we are saying here is that starting with W not equal to 0, you can prove that what this recursive equation boils down to is the following, right? That Wt is actually equal to this formula here. Okay, and remember in the case of L2 regularization also we had ended up with something similar. We had Q D Q transpose into W star, and that Q, this diagonal matrix was, I think, of the form lambda plus alpha I, right? I think that's what it was. I think lambda plus alpha I in something. So it was some diagonal matrix here, and again we have ended up with a diagonal matrix here, right? So what we have done is the following, nothing great. We first derived this formula simply from Taylor series, right? Then we assumed the eigenvalue decomposition and replaced all h's by the eigenvalue decomposition. Then we noted that this is a recursive formula, and in the appendix we have a proof by induction which shows that if you start with W naught equal to 0, and that's a reasonable place to start, and then you compute W1 is equal to this into W naught plus the remaining into W star. This pen does not work properly, right? If you start with this, and this term of course disappears because W naught is 0, and you keep doing this substitution time step after time step, then you will arrive at a generic formula which looks like that, and the proof that this is indeed the generic formula that you will arrive at is given in the appendix, right? So you just take this for face value that Wt can be written as a function of W star related by this matrix here, right? And then I'm making an observation that in the case of L2 regularization also we had arrived at a similar formula. The main difference is that the diagonal there, the diagonal matrix there was a bit different from the diagonal matrix here. There was clearly no power of t in that formula that we had derived earlier, right? But for right now, just notice that this is the same form. You have Q diagonal matrix Q transpose into W star, and now you can show that yeah, here's the L2 regularization, right? So I had it on the slide, I should have just used it, right? So this is what the L2 regularization was, right? This is what the formula that we had derived in the case of L2 regularization. And what was the formula for? The formula for was for the optimal solution for the regularized loss, which was L tilde theta, which was L theta plus omega theta, right? Sorry, this should have been W. Right, so theta and W I'm using interchangeably as the parameters. So the formula for the optimal value for this loss function was this, right? And we have arrived at a similar formula for in the case of in this case also, right, where we are trying to express Wt, right? And Wt is the optimal because that's where you are going to reach after t time steps, and you are going to stop after t time steps. So this formula, these two formula have some correspondence, and in fact you can show that these two formulae are equivalent in this very unique case. If you choose the values of epsilon, t and alpha such that these two conditions are satisfied, or rather this condition is satisfied, then the two formulae actually become equivalent, right? So there is some condition under which L2 regularization is actually equal to early stopping. So we showed it using this derivation, and we also saw it intuitively, right, that what you're doing is you're limiting the number of updates. So limiting the number of updates is equivalent to putting some restriction on how much your W can grow, right? Because even if I assume that every time step W is growing, right? So let me just take a single parameter, right, W. Now the gradient could be in this direction or this direction, but I'm assuming that the gradient is always in this direction, right? And I'm going to restrict the number of times I can do this update. So then I'm not allowing the value to grow beyond this point, right? And in fact, the other case is even more unfavorable, right? Because if the gradient is also sometimes in this direction, then anyways you are going to be even more closer to W than what you were in this case, right? So even if I assume that all the derivatives are positive, that's the case when I'm constantly moving away from W. Even in that case, I have restricted the number of time steps, so I cannot move away from W beyond a certain point. And if some gradients are positive and negative, even in that case, I'm still not going to move away from W beyond a certain point, right? So that's the main point being made here. So it somehow becomes equivalent to L2 regularization, okay? Yeah, so that's all I had to say about early stopping. So a few things to remember are that early stopping only allows T updates to the parameters, right? So now we'll try to get some more insights into how we are also made some other statements in the context of L2 regularization that the important parameters, the weights for the important parameters will not shrink too much, whereas the weights for the unimportant parameters will shrink a lot, right? So does that also happen in the case of early stopping? So if there's a parameter W, which corresponds to a dimension or a feature which is important for the loss, right? If this is an important feature, then the derivatives will be large because the loss would be very sensitive to this parameter. If you change it a lot, if you change it a little, then the loss will change a lot. That's the same as saying that the derivative would be large, right? So if W belongs to an important dimension, then your weights, the derivatives would be large, right? Similarly, if the parameter is not important, that means even if you change the W by a small amount, the loss is not going to change much, which is the same as saying that the derivative is going to be small, right? So now the important parameters, the derivatives are large, right? And you are allowing T updates. Even for the unimportant parameters where the derivatives are small, you are allowing for T updates, right? So now let's look at one important parameter W1, and let's say W2 is not an important parameter, right? So you started at the say 0 for both these parameters, right? Now both you are allowing to update for T time steps because you're stopping the training at T time steps. You're not stopping it for one parameter, you're just stopping it completely. Now for W1, you would have had larger updates, right? Because it was an important parameter. So after T steps, it would have been a slightly larger value, right? Whereas for W2, your updates would have been smaller because it was a less important parameter and hence the gradients were smaller. So after T time steps, right? So here I have taken T equal to 4, right? So after 4 time steps, it's still farther away from the initial value, but this guy would not be very far away from the initial value. So again, you see this proportionate scaling in some sense, right? The important parameters are allowed to grow relatively a bit more as compared to the unimportant parameters. Of course, both the parameters are being clipped, right? In both the parameters are not allowed to grow beyond a certain point, but there is this some kind of a proportional scaling happening implicitly. And the same thing we had seen in the case of L2 regularization, where we had that figure where W1 and W2 were initially some value, right? So say this was W1 and this was W2, and then W both had shrunk, right? But W1, which was less important, had shrunk more, whereas W2, which was more important, had shrunk less, right? So the same thing we had observed there, right? So same behavior actually happens implicitly in the case of early stopping also. Yeah, so that's all I had about early stopping. There are a couple of more topics and we'll come back and do that in the next video.